Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist Tea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire future geochemists and to introduce listeners to niche geochemistry topics. I'm your host, Sam Scher, and this month we're talking with Mark Arundell about the past, present, and future of geochemical sampling to explore how smarter sampling can lead to better outcomes in mineral exploration. Mark Arundell is the principal geologist at IMEx Consulting. Mark, welcome to Geochemistry.
Thanks for having us on, Sam. Lovely to spend some time with you having a chat.
In addition to the hour that we've already spoken.
By 51 minutes, but we won't go into that. And hopefully we won't cover anything that we've covered beforehand.
Excellent. So, Mark has over 30 years of international experience as an exploration geologist, and he specializes in geochemistry, project assessment, and resource generation for precious, base, and industrial minerals. At present, he is the principal geologist at IMEx Consulting, a role that he has held since 2009, where he provides specialist geological and geochemical consulting services globally, covering project generation through resource delineation. Mark, that's my brief synopsis, but for our listeners in search of inspiration, could you tell us a bit more about your journey?
Sure. Thanks, Sam. I did undergraduate at Melbourne University in the mid 1980s, and I got a job with Renison Goldfields Consolidated, which no longer exists, which is a bit of a sad thing, but a bit of a thing that actually has happened in my career. In the first 2 years of that, I actually was on what was called a graduate traineeship, and it's pleasing to see that some companies are still offering a scheme like that. As part of that, I got to spend time working as an exploration geologist. I worked as a mine geologist in an open cut gold mine, and I also worked underground at a copper mine. So after 2 years, I'd experienced all the three components that a geologist could do working within industry. And I was fortunate at the end of that to have the choice of where I wanted to go. And I suppose having that romantic passion to start with, I wanted to get back into exploration. And that's where I landed for the next 8 years within Renison. After that, I made the choice to leave and move to another company. Part of the reason for that was that I wanted to work in porphyry copper. And an opportunity came to work in exploration around the North Parks mine here, where I'm based in New South Wales. And as working with North, I also ended up working on the Cow epithermal deposit. Both of those are now owned by Evolution, but they were owned by a company called North at the time. And during that time, I ended up doing my master's at Codes at the University of Tasmania. And focus of that, like my undergrad, was geochemistry. Pretty much through all this time, I'd worked as a geologist. After North, I ended up at Rio Tinto, where I was there for about 9 years, and probably best way to describe that was doing lots of stuff. I worked in various commodities all through Australia and actually ended up working in industrial minerals. That was partly due to being asked at one stage, could I review potash potential of Australia? And if I was to give people advice, it'd be one of the things is if people ask you a question like that, you say, sure, no worries, love to. Anyway, after the managers had moved away, fortunately, I was able to get straight onto Google and find out what potash was and work out what I just actually agreed to doing. And then I had about 5, 6 years working with Rio in potash in Australia and India. And that actually led to a lot of consulting work after leaving Rio in the financial crisis. And that's where I ended up spending a lot of time in Canada, in amongst other places, including Spain, and looking at projects around the world. Yeah, sometimes it's the turn of a friendly card that don't know how things are going to end up. Rio imploded a little bit with the financial crisis with the exploration division. And so I left them then. Ended up working in the junior sector. I was involved in listing a couple of junior companies on the Australian Securities Exchange here, as well as doing consulting at that time. So a bit of a mixture. Yeah, and that's probably where I got more back into geochemistry. There was some of the work that I was doing with one of the groups where I saw a real need for geochem workshops, just covering what I would call some of the basics, which sort of is what's led to this conversation with Sam about not sampling rubbish. And yeah, I've probably run various, maybe up to about 40 plus workshops over the last 5 to 6 years. Just to be frank, I don't consider myself a geochemist. That's just not because I'm worried about getting retrenched within a company. I'm fully consider myself a geologist with a geochemical bent, if you like.
And I'd like to say to everybody, that's okay. No, I
Yeah,
think
I
yeah, the
think so.
concept of a geologist with a geochemical bent, I see this. I've interviewed quite a number of people like this, and I see this everywhere. And I think as long as there's people that are interested, we're doing good.
It's the best geophysicists I've worked with, geologists with a geophysical bent. Yeah, and I think just having that rounding in the science is a good thing in many ways. Yeah.
Wow, dropping bombs. Yeah, I think my inability to tell different rocks apart would take away my credibility from being a geologist at this point, but maybe maybe a geochemist with a geology bent at this point.
This may yeah, there you go. Yeah, there's true confession coming out there. That's probably the
Right?
reason why that's probably why I got you to read the Dixilito book for doing this podcast as
That
well.
was
So
confusing. I was like, "I don't see how this fits in," but then I was like, "Well, it's speaking to me." Let me just
yeah,
read the title of that one for you guys. So there's 3 papers for this one, but the one that he's referring to is called metallogeny, metallogeny,
metallogeny.
metallogeny,
It's geology 101.
metallogeny and mineral exploration, some personal reminiscences is. Yeah, but it's a forward for geochemical perspectives issue that Dick Silto put out, and yeah, it was just a few paragraphs there, but I was like, "I don't see how this is fitting in, but I feel inspired," so we'll figure that out.
Yeah, I think that part of it is who sees the most rocks wins.
Yeah, big one.
Mm.
Alright, that said, any advice for people wanting to break in?
To geochemistry, I've got
Mhm.
some stuff, and I thought we'd do that at the outro, if that's all
Okay.
right.
Would love that.
At the end, yeah, just give you that sort of walk away thing so that people have a warm glow in their heart.
Okay. Can't give them too much of a warm glow too early.
Yeah, that's right.
Yeah.
They got to last the next 30 minutes of actually having put up the reminiscences of an older person before they actually get something useful.
That said, now it's time for tea. Kettle's hot. Let's hear what you got.
Okay, there could have been multiple things that I chose, but I thought I'd go for something recent and something was about me. So in August of this year, I was involved in running an online geochemical workshop with Richard Lilly from Nexus, which is in the University of Adelaide. There was about 70 people on this online workshop, and I didn't know who any of the people were, didn't get a list of the people of attending, and I think that was probably a really big mistake. And the reason I think when I was talking to Richard about the presentations, he suggested I try and find some recent examples of what you might call poor practice or what I would call suboptimal geochemistry. So I had a look on the Australian Securities, which is like the TSX website, and found a number of announcements and collected maybe half a dozen examples that I thought would probably, let's just say, could have been better. And I added them to my presentation and went through those and explained why.
Excellent.
For example, I thought a 6K long copper anomaly was probably, let's just say, fabricated. Rubbish would be another way of describing it as well. Anyway, a couple of weeks later, I was at a conference and this guy came up to me and he introduced himself and he said he'd been to the workshop and how much he enjoyed it and he had a bit of an accent. It didn't quite, not a New Yorker one like you, Sam. It was a bit more rapid fire, and which made me think that perhaps he'd had some military training. And of course, he was an ex-Marine. He was fairly short, but he was still very scary because he
I'm
was very,
5'3"
very.
or 160 centimeters, and I've been called scary, so yeah. You don't have to be
I
called to be scary.
100%. Anyway, and then he just said, "Oh, those examples that you gave," he said, "one of them was my project." And I went, and Scott Halley was actually sitting next to me, and I don't know whether he actually said it or it was just a voice inside my brain. but it was something like Scott said to me, "This is going to be really interesting." Fortuitously, this guy had taken my constructive criticism on board with respect to his project. He'd reviewed the data after the workshop using some of the methods that I'd suggested from the workshop. And in particular, in this case, it was actually a lot of the copper had probably been scavenged in the soils, and
Mm.
was pleased that it tightened up their interpretation, which recently they've subsequently drilled. And last week they announced that they've hit some massive copper sulfides, and one of the drill holes has hit 80 meters at above 0.5% copper.
There you
So
go.
yeah, so there's a bit of tea that actually ended up with something useful in the end. Whereas if we'd done this podcast last week, I couldn't have added the good part of the story at the end there. But yeah, it's interesting where you can go from a moment of thinking I'm about to have my face rearranged to actually a little bit of joy in the end. So,
No, but that's really cool. And I have to say, you talk about scavenging. We'll just mention it really briefly, but in the last few conferences that I've went to, I have seen a number of presentations that have just tossed data into it drives me crazy when they do it with neural networks. It's completely too much. You don't need that much firepower for just some geochemical data. But anyway, they come out with these associations that are like iron, copper, manganese, zinc, blah, blah, blah. And it's just, yeah, you probably
yep.
have some scavenging. This is not real. Let's move on. But there's no context. People just don't understand that piece behind it. So they get really excited. They're like, this relation is like meaningful. And it's just, it means something.
There are probably two or three things that I see as the biggest fall downs in geochem at the moment in terms of people practicing and sampling. One is sample spacing. The other one is, and I can't remember at the moment, but anyway, it'll come to me eventually. But the third one is, yeah, the fact that mobile elements get scavenged in the weathering profile. And the number of absolute rubbish copper anomalies that I see, for example, is just absolutely appalling. And probably the third thing, if I really, is people using inappropriate technique for the work that they're doing, and there's the consequential amount of money that is just wasted and leading to lack of discovery. People spending huge amounts of coin taking samples, and those samples are basically rubbish. Well,
Speaking on, we're gonna
explore that.
Yeah, we're gonna explore it or all. And for people that aren't excited enough, the whole sample spacing, et cetera, et cetera. One of the other papers that we're gonna talk about here that Mark did with Simon Gatehouse is all about this, that, and the other thing, but they go into how like shows their sample spacing. And I thought that was pretty cool. Yeah, can't wait to talk about all this. Let's switch now. New topic. Let's talk about the show theme. So I guess just something to mention that people are like, "Oh, they talk like they know each other." I didn't know Mark before really this past October when I went to Australia for the first time at the International Applied Geochemistry Symposium in Adelaide, which was such a great time. And really after he tried to rope me into a few things of which he's now achieved, I informed him though that the price of all this was that he had to do an episode. So that's why we have him here and I'm pretty excited for that. And the other thing that I'm really excited about is that the topic that he chose wasn't existential. It's actually really an essential topic in basic geochemistry principles. And we haven't covered it here because nobody else has, I don't know, been interested enough to tackle it or brave enough to tackle it, which is suboptimal sampling. So to start, Mark, can you talk a bit about what you mean by suboptimal sampling and why you are so passionate about it?
Let me answer that first question about why people don't want to talk about it is that there's more opinions than anything else out there in the world. And this episode will go a little bit out on a limb in some ways at the risk of actually offending some people. But probably the best thing I can do is to start with a story, because stories are always make people a bit happy about things. And I do a lot of work on looking at discovery and seeing companies trying to be as effective as possible. And there's this mantra that discovery is declining, exploration is costing more, and it's all because of all the government regulations. Yeah, where I'm standing and looking at what companies are doing, I think part of the problem is that we're collecting what I would call rubbish or suboptimal samples. And therefore, that actually leads to drilling targets that are probably not the best things that could be drilled. And this goes back to some work that I did on a project about 5 years ago, where an explorer in the area had collected about 1,400 minus 80 mesh soil samples on a spacing of about 400 by 80 meters. I found the data extremely difficult to interpret. It didn't seem to hang together at all. Had little coherency, it was spotty, the values were patchy, and generally the material or the values were quite subdued. So what I did is what I normally do, and if a client asks me, I put together a regolith map, and we'll talk about that a little bit more if Sam wants to explore it.
I
And
do.
using, oh, good, using Sentinel data, which is
Mm,
a satellite system from the European Space Agency. And the thing I love about it, it's free and it's 10-meter resolution. And I call regolith mapping a bit of a lost Jedi. It's not exactly a Luke Skywalker thing, but putting a map together to actually guide your sampling, I think is an amazingly simple thing to do, but is extremely powerful as well. And while doing that, I noticed in this particular area that the spoils from the dams was very different in its spectral response to the paddocks. And that sort of it ended up being a bit of a clue that something strange might have been going on. Anyway, while driving around on the public roads, I pulled up because there was a bit of a gravel scrape on the side of the road. Do I need to actually explain what a gravel scrape
yeah,
is?
let's do it all. Every
Oh,
rabbit hole,
okay.
no stone
Yeah, yeah.
unturned. Yeah.
So it was basically a bit of a hole on the side of the road, and gravel scrapes like road cuttings or dams give you the one thing that you mostly don't get in exploration geochemistry, a vertical perspective. And what I noticed by crawling into this gravel scrape, which I've taken a number of people to, fortunately at the time it was dry. I've taken people in there, this particular one, when it's wet and it's not very nice, was that the bedrock in the area, which Canberra Ordovician was about maybe 30 centimeters to a meter below the surface. But the soil that was above that was what I would call a red aeolian sand or louse. It contained rounded ferruginous material as well as quartz gravel, which I think now is actually possibly Mesozoic in age. But anyway, that's an aside. But what was really apparent was this horizon was not in situ. It was not a soil developed on top of that weathered bedrock, like. And basically, it should be geochemically inert because it's actually exotic. So if you sampled in the surface in that particular area, you would get zero bedrock signature. Anyway, so this started me on mission. So if you did minus 80 mesh, if you did minus 2 mil, didn't matter what you did in the surface in this particular area, you would not get a geochemical response. However, if you drill down, and it's almost embarrassing, a meter, you would actually hit bedrock samples. And I can remember when we started the auger sampling, we started in a valley, and I thought, well, this is a good place to start. The guys will have to drill down quite a way before they actually get any rock. They got down 10 centimeters in underneath the material and actually went straight into bedrock. And as we went up the hill, the cover got thicker. So the terrain actually had an inverted terrain in this particular
Interesting.
case. Yeah. So it was really interesting in terms of here we were using the sampling and it was constrained by the regolith. Now, this is where I get dangerous because I know Sam doesn't like this. This is what I call orientation. Doing the regolith map, field checking it to determining the optimal sample medium. Didn't go out and collect 5 different soils, sieve fractions, didn't go out and do 5 different methods. This to me is quality assurance. And I didn't really understand what quality assurance was until a couple of years ago when I was forced to do a course on it because I thought QA/QC was basically tidying up the mess afterwards. But QA, quality assurance, is trying to make sure you don't take a rubbish sample. It's maximizing your sample effectiveness. And I'll use an analogy later on where something I know nothing about, which is golf. To me, it's choosing
Yeah.
the right golf club, basically. And it should be fundamental to how we operate as explorers or even at university when we're taking samples for our theses and that sort of stuff. We need my one bugbear, I'll throw this in. So many papers are written with great geochemical data, and there's not an XY with that sample. A coordinate with that sample gives it a spatial connotation. Geology is that spatial connotation. Anyway, so all this rubbish sampling basically feeds into the cost of discovery. So yeah, QA, QC, we'll touch on about that. I'd like to talk a lot about the quality assurance part because if our initial samples are bad, it doesn't matter how much QC, quality control, you do on it. If you've collected rubbish to start with, it's that rubbish in, rubbish out type stuff.
Totally. And I think, though, you mentioned university, but I think also it's well established that in every university that exists for geology right now, that you learn a lot of theoretical, there's very little practical. And so we can't continue to look down on people for, I'm not saying that you did, but look down on people for, what do you mean you don't know how to do QA or to take a sample or something? I remember my first geochemistry job and just, oh, just go out and design a program, and me being like, this is overwhelming because here I am. I went to university in Canada. Not that I would have understood how to make a till program either, but I was in Chile and you have, you have the Atacama gravels, which can be a kilometer thick. And it's just this whole thing. There's mines all around you. So you have that component with the additional pollution and everything. But it's, you can't just,
Contamination. Yeah.
exactly. So it's just, we have to stop treating this, what do you mean you don't know? And just be like, we can turn you to this resource or something. So that's something that I think that we need to cook up in a separate place, actually, maybe.
Yeah, I mean, it's like this example here. There's 1,400 samples that were taken. I would
Mm.
say 95% of them are rubbish. That company's not only done that, but they've wasted over $130,000 in
Yeah.
actually doing that, just to start with. And if they decided to drill any of the targets from that data by imposing a statistical threshold into that data, they're not going to intersect anything and then think, oh, okay, we've done the job, we've tested the target, haven't found anything, move on. But when you'd say, I'll try and use an American example, say when you're
Ooh.
in Washington and you're sampling material from Arizona, you drill it in Washington and the material that you've used for the soil sampling has been derived from material in Arizona, then you're really wasting your time. Yeah, and I think people recognize that to a certain amount, but I still see a lot of sampling, and I've got another example which we'll come to later,
Can't wait.
where yeah, 40% of the samples that were collected 2 years ago. So this is a very recent phenomenon. Let's just say suboptimal, keep it nice, and it was $250,000 was what the company wasted with that.
Maybe really quickly, an aside for me, I turned down a job because it was a very incredibly tightly, it didn't need to even be that tight, the sample spacing. It was so tight. But they asked me, you know what superfine is, which is a whole
Yep.
different thing to that we could touch on. But anyway, I was like, yeah, I know what this is. We did it based on that. Can you interpret this? And I was like, yeah, but I need to see this and this because I know that this stuff came from some desert somewhere. And they're like, I don't know if they just thought that it was too hard or they couldn't answer those questions or they just wanted somebody just to just look at the data and give them an answer. And they were just maybe mad at me that, number one, I wouldn't come down in my rate. And number two, that I was asking them of things to interview them to be my client because I was like,
Yep.
"Mm." But again, another really expensive, that survey easily cost them 200K. Easily.
Yeah. Easy.
Yeah.
The first question I ask clients these days is, and it's a great question to ask, is what are you trying to achieve? And then start from that. Do you want listed chemistry out of your data? Do you want to get alteration out of your data? Do you want to just get pathfinders? Or are you just looking for copper and gold? And look, it's fine if you're just looking for copper and gold. But yeah, don't expend money on doing Pathfinder geochemistry if all you want to do is find copper and gold. Understand what your objectives are before you actually start the sampling program. And then the other thing, which we'll come back to as well, is how big is the ore body? What's the footprint that you're actually looking for as well? Yeah.
Said, let's get into this Q&A. I can't wait. It's just going to get more and more nerd. I love it. This is referencing one of the other papers that we had called Why 80 Mesh by Robert Garrett from the Explorer magazine. from a few years ago. It follows the history of how quote we came up with minus 80 mesh, but it's really interesting. Go read it. How has the evolution of geochemical sampling techniques, such as the introduction of the minus 80 mesh fraction, shaped the way that we approach soil and stream sediment sampling?
That's a really good question. And yeah, the Garrett paper actually came at it about the same time that I've been doing this work and that example that I just mentioned previously. And it was great for me to see that because it just made me ask the question, why were they using minus 80 mesh in that particular area? It didn't matter what technique you would have used on the surface there, you probably still would have got negligible results. But it was interesting to see how minus 80 mesh developed. And to me, like with most geochemistry, it's relatively recent. It was in the late 1940s, early 1950s, where they recognized that this fine fraction of about minus 80 mesh had two great advantages. And one is that it concentrated copper, which sort of makes sense because clays tend to pick up, the clays have a negative charge. They tend to pick up cations, and that's something we'll come back to as well. And also, the other thing I think a lot of people forget now when they do minus 80 mesh is the idea initially was it saved grinding the sample. So it saved you that step of sample preparation. And if people wonder why the assay lab rings you up after you send your minus 80 mesh samples in and saying, why do you want them pulverized? There's a good reason for that, is that minus 80 mesh was actually developed as a way to actually avoid this pulverizing stage or sample prep stage to decrease cost. And they basically found that in this fine fraction, the minus 80 mesh, it was basically about the same as what you get from what they considered at the time to be a minus 2 mil, sorry, a standard sample, which is minus 2 mil. There were other experiments done which showed very little variation with the size of the sample. So basically, minus 80 mesh produced about the same results that you get from minus 2. Sometimes it was actually better. But probably one of the main things, which I didn't realize until I read the article, was it saved the sample prep stage. And that was probably one of the big reasons for why minus 80 mesh took off initially in the 40s and the 50s.
It makes total sense, and I can definitely say that I've been guilty of putting in the prep stage too, just not having the history behind that, and having received that call. Do you really need this?
It's we do a lot of stuff because this is how we do things, and we don't
Mhm.
know why we do things a lot of the time. It's just standard operational procedures, maybe, or just we just don't know. Simple as that.
Could you share then how methodologies pioneered by the USGS and other field pioneers have influenced the way that we've approached terrains today?
Yeah, it's interesting because I wondered why did minus 80 mesh become so popular, and it's probably the simplest thing is they published their work, and a lot of it was published in economic geology, and that was widely read by mineral explorers around the world. So when you actually put it out there and people see it as a good thing, and let's be clear, it was successful, but for copper, lead, zinc in particular, nickel, cobalt, we're getting into these cations here basically, and there was a lot of orientation work done, but it was people like Lovering in particular. But a lot of this was a bit post hoc in some ways. But these generally confirmed that minus 80 mesh was a superior fraction for soils and stream sediments, both in detailed and regional reconnaissance surveys. But I think the really big thing was that the data was published and people saw it. And when you actually start seeing that, it becomes quite easily adopted in that regard.
That said, in addition to the publications, the minus 80 mesh, were there like some critical geochemical turning points in exploration that were set that are foundational for today's practices?
Yeah, I think with respect to minus 80 mesh, the application of it in Africa, it was used a lot in Australia and I guess throughout America because that was when it was originally adopted. And there were a lot of case studies showing that it worked in terms of discovery in that regard. There's no sample preparation, and there was a ye field analysis method called the colorimetric technique,
Mhm.
which is what I call the PXRF from 50 years ago, which basically, was a field kit with a relatively high detection limits, but could actually tell you whether there was, I think, copper, zinc, maybe even nickel, and possibly did lead. And it was field tests, which is interesting because, again, that was something I didn't know about until I got delved into this. And yeah, you can still buy the colorimetric testing kit. So if you want a ye olde sampling method without actually having to pay 50 plus grand for a PXRF, sorry, PXRF people, see if you can dig up a colorimetric technique if you're just going to do basic soils or stream sediment sampling, and you can do it out in the field with your -80 mesh samples. So it's, yeah, came very it definitely, if you like, foundational in terms of our exploration practice. But yeah, it's fascinating to see why did we actually forget why we started doing this in the first place.
Such a good point. And I know coming up to this next question that you cannot wait to answer it. So here we go. Standard
I,
practices such as this -80 mesh, are they still universally applicable or should we still use orientation surveys?
Yeah. So what I'll
Yeah.
do is into the valley of death walks the 12 brave. What I'll do is I'll soften the blow by start off by something that Bob Garrett said. And he basically, yeah, pinned it. Over the last 70 years, we've used -80 mesh for soils and stream sediment analysis. It has proven effective. It's led to the successful discovery, basically a base metal mineralization. But then he puts this rider in about we shouldn't accept that -80 mesh is the be all and the end all. And he talks about doing directed orientation work, which may show that a more suitable size fraction for, and he does pin it out in terms of specific trace elements and mineralogical conditions, in particular precious metals like gold, that -80 mesh may not be appropriate. So if I was to answer that question, I would basically say to you, Sam, the answer is yes and no. And to me, it comes back to that question I mentioned beforehand. What are you trying to achieve? So just let me touch on orientation surveys because this is something I have different thoughts on, which to me is fine. I look at it as a statistical sampling in terms of actually getting enough reasonable samples to actually get enough of the data set. If you were doing orientation, you could do various mesh sizes and you could do different analytical techniques, say 5 different mesh sizes, 5 different analytical techniques. If you want a statistical viable number of samples to actually get rid of some randomness, you probably need to collect 100 samples. We've got 100 samples, 5 different analytical techniques, 5 different meshes. We've got 2,500 samples. With the time that someone maybe has to collect them and do all the sieving, it's going to cost you, say, $250,000. I think just with a regolith map and spending some time out in the field, we can achieve probably about 80% of that, what you might get from the different analytical techniques and the different sieving techniques. And yeah, basically do it at the field for a fraction of the cost and also save you that time in terms of having to wait for the samples to come back from the lab and then doing the interpretation on that.
And I think though
What do you
you
reckon?
I was gonna say, I think though you also had a really interesting way that you did it in the article that you and Simon put together about the Sofala deposit. Could you
Yep.
wanna talk a little bit about that?
It was a thought experiment. Yeah, we went
The
through the
thought
process.
experiment, yeah,
Yeah,
of
yeah.
just, like, really I guess in that sense, really quickly then, the thought experiment of just being like, "Okay, so in this Sofala area for everybody that is unaware, which is me and probably most of humanity, you had all this artisanal and old mine workings and everything, and it's a gold area." And so really the thought experiment that I'm thinking about right now is just that okay, all the coarse gold is probably going to indicate places that have already been mined and that we already know about. So, how do we get down to that fraction that's going to contain the fine gold? And that seemed to me about how you were choosing some of your sieving sizes as well.
Definitely. Yeah.
Yeah,
So we did the orientation without collecting a sample, I suppose is how
fascinating.
I would describe it.
Yeah.
And to me, this is the same thing as doing the regolith map and
Mm,
doing the field checking. You're actually doing your orientation without collecting a sample. And I think that's cheaper And I think that's geologically more effective. And that's why I told that story about the -80 mesh stuff where I wandered out and I had a look at the dams and I found my most favorite gravel scrape in the whole of Western New South Wales. Because just even finding that, it was like the aha moment in terms of it actually explained everything that I needed to know about that area. And yeah, and all we did was confirm it by doing the auger drilling as well. The most annoying thing about the auger drilling was that some of that cover was actually shallower than what I thought. If the soil sampling had gone down a little bit deeper, they may not have had as many issues with the samples in through that area. Yeah,
So then, and I think this is a theme through a bunch of the articles that we read too, but is how does understanding regional geologic controls enhance then the design of effective sampling programs?
sure. Yeah, I would throw the word regolith in there as well in terms of understanding that. And yeah, if we're talking about, say, doing conventional soils rather than partial, some of the lower detection or lower digestion partial leaches, to me, avoiding sampling thick or possibly even thin, what I would call non-transmissive cover, is imperative. Avoiding the material where you're not going to get a geochemical signature or it's geochemically. The question I'd ask is why sample material where you think you're not going to get a signal? So my first thing is to avoid those areas. And you may find that the whole area is like that, as we did in this particular example that I mentioned. So if soils are ineffective, you may need to go to auger, or you may need to go to air core or RAB or some sort of bedrock type drilling. Or there are areas in the converse where the soil is actually not developed and there are rocks sticking out of the ground. And this is one of the funny things I've found with a number of clients where they'll actually send someone up to actually take a soil sample and our crop's 90%. Areas in
Yeah.
Canada and Finland where we've got scraped terrains or even, yeah, some places in Australia in the Mount Isa area, there are rocks sticking out of the ground. Trying to take a soil sample in that area is very difficult. And part of that's to my mind in that ruthless, cost-effective explorer. What is the quickest, simplest way of actually taking a representative sample of the material in the ground? That may well be a rock.
Good point. What methods can help distinguish between meaningful anomalies and misleading signals, such as coarse grain versus fine grain gold in stream sediment sampling?
Oh, yeah. So this comes back to the Sofala thing. So Sofala is about, let's say, 200 kilometers west of Sydney. It was one of the areas where gold was originally discovered in Australia in 1851. So that's why you've got so much historic production in the area. So the artisanal stuff that Sam talked about. The other thing besides the artisanal one is that we get these quartz vein gold systems where you get that coarse grain gold in it. And these would produce an anomaly in soil sampling with a technique called BLEG. And I was going to talk about this coming up because this question coming. But so in the area, the problem with BLEG is that it samples all gold. So you'll end up with the alluvial, the coarse grain, and the fine grain gold. But what we were trying to target was disseminated gold or fine grain material that the old timers wouldn't have actually found. Yeah, going in here, and it's counterintuitive because normally with gold, you take as big a sample as possible because of the particulate nature of gold. What Simon found from the modeling that he actually did was that the fine grain gold, the finer you actually got, the less particulate it behaved like. So you could actually go to a relatively fine mesh. The neat thing happened here, and the story would be absolute rubbish if we actually hadn't have found the Spring Gully deposit, which was a disseminated fine grain gold deposit. Yeah, so things can be done, but I love the story basically because it's a counterintuitive approach to actually sampling in through that area. The other thing we actually did find out is that these coarse grained deposits or prospects actually have fine gold associated with them as well. So that was something we didn't actually expect to find, that be it fine gold, 4 to 5 micron, if you like, does actually hang around even where you get some sort of, in inverted commas, nuggety type materials, plus 100 micron type gold as well. Yeah.
Look at that.
The yeah. And look, and if we want to talk about other style of deposits like copper and lead, this what you're talking about meaningful anomalies. The other thing I'd be using is iron and to an extent maybe manganese and aluminium. if we're looking at base metal type deposits, to actually help reduce the number of misleading signals, or what I call true anomalism in that regard. Because iron scavenging, particularly if you've got something like mafic volcanics, you can get quite extraordinarily high copper values to 0.1, 0.3%. It's one of the exercises that I use in the workshop, which, always trips people up because we tend to be high number type people.
Hmm.
Um, it's, as you touched on earlier with some of the data science type techniques, they don't necessarily account for scavenging particularly well when you just throw lots of numbers into the box. Yeah.
Yeah. Meanwhile,
Let's move on.
I know. Let's move on. I was going to say, meanwhile,
Sorry, sorry, sorry.
No, I just gave at one of the workshops in IAGS this past October. I gave what I thought was a really cool, more like thought experiment too, with a little coding thing that I did with a friend of mine, where I looked into how can we better quantify the effects of iron and manganese oxide scavenging. And so it's just one thing where people use like coding and data science to just be like, oh, look at these relationships that we have. And I was just like, how do we remove that? And so it's like this kind of inversion. Anyway, data
Yep,
science is
yep.
cool. You can use it for good.
Yeah.
Uh,
Look, I'm sure you can. But I find if people don't understand the concept behind it
yeah.
beforehand, then the application of it tends to be suboptimal,
Subpar.
shall we say. Yeah.
Close.
Yeah. Yeah.
Yeah. So building on what we were talking about, how do modern geochemical sampling protocols balance the need for cost effectiveness?
Well, at the moment, I would say the diametric opposite. I think we're actually becoming less effective with our sampling, and the cost is actually increasing. The number of times over the last 4 or 5 years where I've been involved with companies where they've had to reanalyze material. And you can actually see it if you go through TSX and ASX releases with company that they're actually reanalyzing their material. Actually gave, and I'll plug a good friend Jess Keast here. I gave a GeoHug talk on this, I can't remember, it could have been last year, about reanalyzing material from the 1970s. And that was phenomenal to be able to use modern ICP-MS techniques, and revealed a huge amount of hidden information within that data or within those samples that the company was basically unaware of. And a lot of things fell out. Multiple targets fell out as a consequence of that as well. And it's, some of the work I'm most proud of because it just really worked extremely effectively, but was using the right geochem protocol for what we were trying to achieve.
So, how do properties of different metals influence sampling protocols, analytical methods, or interpretations?
That's a killer question. So what I'll do is talk to this one with an example. It's a porphyry copper gold prospect that I worked on. And basically we have mafic to intermediate volcanics and intrusions. So when they weather, they form dominantly a clay fraction. There were over 300 samples from this area. And it's I've got about 10 or 20, not actually about 20 of these now, where I've got replication of minus 80 mesh, which is 180 micron or 0.18 of a mil, and minus 16 mesh in this particular case, so minus 1 mil samples. So it's really interesting to see that the cations in particular, copper, lead, and zinc, show good agreement, basically one-on-one correlation. So it wouldn't matter if you use minus 80 mesh or minus in this case. For me, because I'm the scumbag geologist, I want to use the sample method that as quick as possible. It takes me much longer to sieve a minus 80 mesh sample than a minus sample. So the difference may well be I can collect 80 minus 1 mil samples in a day, and I might be able to collect 15, 20, maybe 25 minus 80 mesh. Yeah, you need to factor that into your sampling
And
cost.
to interrupt you right there, too, I think something to think about is that people will be like, oh, but it will cost $10 more in the prep lab. So I'm going to save money and do the sieving myself. But whomever is sieving, you're also paying.
Yep,
Time is money. So maybe,
yep.
in fact, you may be saving money and sampling faster and all the things by just doing it at the lab. So,
One of the classic sayings from my dad is it takes a lot of money to save a little bit of money. But
There you
the,
go.
the, the inter- yeah, the interesting thing about these samples is that they actually, besides copper, lead, zinc, they analyze for a number of other elements, and they were focused on gold. And because of me being bent in the direction of pathfinders, I wanted to look at antimony and arsenic and a lot of the other ones. A lot of the other pathfinders were below detection, so I just removed them from the data set. The thing that really shocked me was how low the oxyanions and gold were in the -80 mesh. So on average of that 300 odd samples, and the variation could be more than 400% on individual samples. On average, gold was 45% lower in the -80 mesh, antimony was 50% lower, and arsenic was about 15% lower. And look, got to ask the question, and it ends up being a bit of a Homer Simpson thing in terms of -80 mesh. Cations good, oxyanions bad is probably how I would do it. And look, clays are negatively charged, so they're going to attract a positive charge. So that's the simple story, I think, behind that. Now, in this particular case, and you spoke about it, yeah, they didn't actually pulverize the -80 mesh material, which may have caused some of this variation in the sampling. I doubt it. And it also would have cut down the saving that you're supposedly making by not prepping it. But you would have also annoyed the lab as well, because it's really hard to clean out a -80 mesh sample out of a pulverizer. As you touched on there, basically sieving to that finer mesh has actually negated pulverizing at the laboratory. So it was a false cost saving a measure in that regard. But the big saving, I think, is that if you can collect 80 to 100 samples a day at minus 1 mil, rather than that 20 samples a day of -80 mesh, that and people are not cheap, as you said, they're
Yeah.
actually in the field there. If it comes and it reverts back to that question, what are you trying to achieve? If you're after copper, lead, zinc, fine, do -80 mesh. If you need the pathfinders, and I think honestly, you do, then you really are potentially, and I'll say potentially because don't want to upset people 100%, because I'd love to say you will actually be missing out on so much data if you're actually not taking that course of fraction. However, if it's an aeolian environment, you actually need to start thinking about whether that's an appropriate technique to have. And that's a whole nother story we could talk about for ages about
Oh my
lag
god.
sampling. But yeah, we can move
Yeah.
on.
Ooh, I have so many
Did you like
thoughts.
that one?
No, I like that one a lot, and it was great to do with this example,
Yep.
um, because I think it just made it more real for everybody.
I,
People will let
I've
us know in
got,
the comments if they felt the realness of it. But yeah, no, that was
yeah,
super helpful.
got another two examples where, yeah, I've got ultrafine versus -80 mesh
Please.
versus the lag samples, which I've hidden down the bottom here somewhere because I didn't think we'd get around to this. But as soon as you're enjoying it so much, Sam,
Oh my
so
god, I love this stuff. We're all about rabbit holes here.
so it was interesting. Well, actually, I've got two examples here. One's a quick one. So it's comparing -80 mesh versus -1 mil. And what really surprised me is in this particular area, and it's the regolith regime that's smacking it, the cobalt results are a third lower in the -80 mesh. Chrome
Okay.
is a third lower, and iron is the third lower in the -80 mesh. Yeah, as an average. Uh, It very interesting. So in the other area where I've got lag versus ultrafine versus -80 mesh, in looking at lag versus 80 mesh,
Can you just tell people what
uh,
lag is?
so lag is like what I'd like to, if you go Irish, they're the little rocks. Uh, the lag's defined in various ways, but it can be between -2 mil, sorry, +2 mil to say -5, 6, or -7 mil. So it's just very small rock fragments in that regard. And if you're in an aeolian environment where you actually have quite a lot of sand, it can be the ideal sampling method. So yeah, so you can, some people call it a coarse grained soil, which I find odd. Anyway, whatever you want to call it. So just in this example here, the the values in the lag, silver was 74% higher, arsenic 200% higher, bismuth 100% higher, moly 200% higher, copper 100% higher. You can see quite significant variations. And these are people doing orientation very kindly. But when you actually go out and have a look on the ground in these particular areas, which I have done for this particular case, and I had my snotty face on saying, my God, why would you take -80 mesh in this particular area? Because it was very similar to that example I gave earlier, where you could see it was aeolian sand and louse, and there were ferruginous pebbles as well as quartz pebbles. Um, interestingly, I think that's Mesozoic material. And that was 3,000 kilometers away from that first example that I talked about earlier today as well. But a very similar regolith regime as well. And so it brings back that importance of getting what I call the dumb geo to actually walk the ground and having a look at the dirt, basically. Yeah. Sorry, an aside. Let's go
No,
back.
love that. We love, like I said, we love our rabbit holes because nobody ever talks about this stuff, right? So that's what we're here for. Stuff that nobody talks about. Maybe nobody cares, but we care.
It, yeah. I think to me, this is all very fundamental stuff because in exploration, if we're trying to find stuff. Yeah.
Agreed. So, how have any analytical advancements, for example, and I think we've talked quite a bit about this, but getting ICP, MS from OES, different digests, et cetera, contributed to reducing suboptimal sampling outcomes in geochemistry?
Yeah, I think I've been thinking about that, and I think that some ways we've gone the other way, that we've got these great pieces of kit available now, and the labs come up with these new things and say, we can do this and we can do that. And they're generally really good at recommending an appropriate technique for what people want to do. But the thing that's missing is that the lab doesn't go out on the ground. The geo does. And so the mistake I see being made, and people blame the lab, is actually people aren't familiar with the regime that they intend to sample before they actually speak to the lab about the optimal sampling methodology. And yeah, we're getting better with our analytical techniques, but I think we're getting worse in terms of determining what the optimal sampling methodology might be within the area. So I'll answer the question by flipping it around in some ways there, that, yeah, we'd love technology. Everyone loves the latest new phone and that sort of stuff. I would love to get myself a flip phone because I'd love to go back to a clamshell, but I can resist that temptation. Oh, come on.
They have,
Uh,
what is it, Samsung has out there? They got
yeah,
a flip phone
yeah,
if you want
yeah,
that. There you go.
yeah, yeah. It's just when it was $2,500, I went, yeah, nah. Anyway, but yeah, but even I get the glittering lights and that sort of stuff. I get attracted by, but the reality is it's still a phone and still does the same thing as the phone that I got for $300 whenever it was 3 years ago. And look, let's be honest here. It took many years to actually drag me away from the BlackBerry as well. Yeah, I do some of my old tech in that regard.
I mean, they
But yeah,
dragged away from themselves.
yeah, good movie. But we've got much better in our analytical techniques. We can, with ICP-MS, we can see things and deposits that we never saw before. However, we've got to make sure that the sample material that we're collecting is appropriate for doing that type of work to start with. Yeah.
And then I think similarly to how we're talking about this, I think the next step talking about how we interpret data, um, what role do you think that may ML play in reducing suboptimal sampling outcomes in the future?
Yeah, and look, it took me a while to reflect on this as to whether I could give you an intelligent answer to it. And I've been working with a group who've used machine learning to actually do regolith interpretations. And I was very doubtful first because I like to cling on to things and do it the old way. However, I was really impressed with the ML learning because basically once we fed in a bit of information into it, it was able to go through the rest of the scene, and it was a full 70 by 70 kilometer scene, and probably got 80 to 90% correct through there. Which is that as good as a human? Probably, I'm not sure. And probably quicker as well than what a human can actually do. The thing that I've reflected on afterwards about thinking about it is it removed the geo connection from the interpretation. So just looking at that Sentinel false color scene or the Google map thing of the aerial photo or something like that, bits and pieces that you'd see in that. Oh, okay, so I need to go 100 meters away from that dam and I can see it because I've interpreted by drawing a circle around it. Whereas if the ML had actually done it, all you do is get the output and then you go and follow up the output basically in the field. So there's a step, I think, where ML is extremely useful in that regard and produces a really good first pass product. But I think we need to actually get the geo involved in it. So that's just talking about in terms of the regular stuff. Do you have any thoughts in terms of just whether we should throw data at ML and just let go to rip?
I think when I first wrote the question, I was thinking about, is there a way that we can say, okay, I'm looking for this kind of deposit? So something that maybe is more longitudinal. So we're thinking about
Yep.
long kind of shaped
Yeah,
deposits. We're
yeah.
thinking about the type of not just vegetation, but also the subsurface input that, like things that we know about that. And then I'm looking for a deposit of this magnitude, and maybe there's other inputs in there. And then ask the model to then to propose maybe some sampling schemas of, okay, I think that based on this and this, you should do hexagon grid spacing at this, and then whatever other caveats. Just asking it maybe to help the geologist, the geochemist, to plan a more effective survey dependent on the environment they're in and what they're looking for. That's
Yeah,
maybe
yeah.
I was
Yep.
thinking something like that too. But then
Yeah.
also, as you say, with the regolith stuff, then taking that into consideration, I guess Canada's more till, but we know in that
Yep.
area, we know we're in this one area of Northern Ontario, we know that there's 3 distinct till layers, and which one from the literature, as GSC puts in a lot of stuff, do we know is best for sampling, and
Yep.
how
Yep.
far down do we have to go, and put
Yeah.
in the
Yeah.
economics to it too. Maybe there's something in that. Is this a business plan that we're dreaming up right now?
Yeah, I think so. To me, till is reckless.
It
Till is
is.
no different to what
Yeah.
I deal with
Mhm.
here in Australia, except yeah, it could be let's say a lot darker. Yeah, so some of those organic layers just really freak me out when you come from red dust and suddenly you've got all this black mud and you're down there. You go, wow, I'm not in Kansas anymore. I'm in a totally different world here.
My
But
favorite
you know,
I was just gonna say real quick, my favorite I took this great till course, but I had come from the land of the Atacama gravels, and they're just like, "Oh,
oh,
till you might have to drill 10 meters or something." And maybe I'm just being an asshole, and maybe it's a little bit deeper than that. And I was like, "I'm talking about a kilometer thick package or
yeah.
more here. Like, 10 meters, give me 20, whatever, who cares?"
And look, and part of the reason I love the Atacama is because it came up with one of the few stories of sampling in transported material that actually, with respect to spents, where you actually have a near surface signature. And I'm going to forget her name, but Ali,
Allie
who I
Brown.
think's now with,
Mhm.
yeah, was doing that work with tech and looking at the salts and that sort of stuff. And I thought,
Yeah.
you've got a mechanism to get the material up to the surface there in the Atacama. And then the stable platforms like a lot of Australia and the Superior province in Canada, you don't have that. And it wouldn't be great if we had a few more earthquakes in those areas to get the signal to the near surface.
Maybe we just gotta have a fracking company too. Fracking for geochemical exploration.
I'll say, next question, please.
Okay. Reflecting on the work that you've done at your projects, including the Cephalus paper that we read about, do you have any lessons that stand out that could guide modern exploration efforts?
Yeah, I think when I look back on the Savala thing, which, is embarrassing, was 30 years ago, and you start realizing the best work that you did was before people like Sam were born. You
I'm
need
over
to,
30, but
oh,
then
okay,
also those figures were funny looking.
thanks.
You're
Um,
welcome. Continue.
Thank you. You need to identify the problem early on, and that's why I love asking the question, "What are you trying to achieve?" And look, we were fortuitous within RGC that we had Simon Gatehouse there, who had the softest, gentlest way of challenging you. And to come up with an idea that could even convince management to do something totally different, some sort of counterintuitive approach. We talk about the fact that we want to do things differently, think differently, and that sort of stuff. But we are fairly conservative, I think, in a lot of ways with our exploration. Yeah, the number of times I've heard people embarrass themselves by saying, "Oh, yeah, but we've always done it that way," and then say, "Can't believe I just said that we always do it that way." But we just get into ways because someone shows us how to do things, and therefore they believe that's the best thing to do. The more we actually challenge ourselves, the better it is. And yeah, so we've touched on the thought experiment, if you like, with the Savala stuff was great. And Simon went off and did conditional simulation. This is 30 years ago. The science did exist then. Some people may not believe that. But yeah, and it showed that a certain mesh size would actually work, that would be the best for it. And the other thing which we didn't touch on is that when we analyzed the samples, we actually analyzed them twice if they were above 10 parts per billion. And what we were looking for was not the highest value, it was the most reproducible samples because fine grained gold should have reproducibility. So the more reproducible the samples were, the more likely it was coming from fine grained gold. If it was less reproducible, then it was likely to be coming from coarse grained gold. So
Right.
even with the fine mesh, the 120 mesh that we were using for the sieving, that didn't negate that coarse grained gold would through, but it just meant it was less likely to get through. Yeah, there was all sorts of lessons through there that, dare I say, 30 years later, I'm starting to appreciate now. Yeah, identify what your potential problems are early. Just don't go out and sample, which I think's the problem people have.
And I think the question that I want to end on here is, and I think we've talked about a lot of them already. So feel free to just maybe skip over a few of these bullet points that you've given yourself notes for. But I think there's still some that we can chat about, which is what do you think some of the biggest pitfalls that geologists, geoscientists, geochemists will face in sample design? And I think maybe you typed in or inheriting legacy data sets, but also how can they be avoided?
Sure. I fortunately discovered yesterday that I'd stolen something from Mark Perlow and Amanda Stoltz from ALS. And it's a really good question. How big an ore body are you looking for? Do you know what the size of the deposit actually is? What's the footprint that you're hoping to detect? Is it just the mineralization? Is it the primary dispersion or the secondary dispersion? And that will help you determine what the sample spacing should be. And also, how many anomalous samples would be willing to follow up? I'm happy to follow up a single point sample. So I'll actually try and make my sample spacing as wide as practically possible to reduce cost, basically in that first pass. If I'm looking for an Olympic dam, which has got a footprint, say, of 10 square kilometers, I'm not going to do 100-meter by 100-meter sampling. However, I have actually seen 100 by 100-meter sampling with someone actually looking for that. That's just not appropriate. We've talked about, yeah, what's the optimal mesh size? Do you need to be conscious of whether there's alien sand or other dilutants present? With respect to legacy data, is it what you actually want? Does it have the pathfinders? Does it have the alteration that you might be looking for? Yeah, there's lots of things that can be done. And I think one of the big things is to actually put this regolith map together. It doesn't have to be high class. You don't have to show it to anyone. I'm not going to rate people on it. The other thing is if your sampling is going to be, say, on 200 by 200-meter samples, then your boundary only has to be as close as 200 meters, basically. So you're allowed one or two samples out into the transported regime. No one's going to be too upset about that. But please don't spend $250,000 and 40% of your sampling costs on material that's just basically wasted. Yeah, I'd probably, I'll finish. Oh, do you want me to finish up on there? If you like, asking the
Yeah,
question.
finish up. Yeah, finish up
Yeah,
on what your the rest of your feelings are. Just tell us them all. Let's go.
well, I think I call it the red pill in some ways. So it's going to the matrix. Do you want to discover the truth, basically? And it comes to that, what are you trying to achieve? And I'll use the analogy of gold for it, because as I said, I know absolutely stuff all about it. And I talk about the hole in one, or that's the ore body is the analogy. If that's the case, you're looking at direct detection of mineralization. That's fine. You might be looking for gold, look for gold if you want to directly detect the mineralization. Are you interested in a near miss? Okay, that's the green. You're landing somewhere near where the hole actually is. So that's your pathfinder and your alteration geochemistry. If that's the case, then you need to alter your analytical method and possibly your sampling method as well. Are you on the fairway? Are you actually within the right rocks? And that's your list of geochemistry. Are you heading in the right direction when you're teeing off and that sort of stuff? To avoid being in the bunker or the lake or on the wrong fairway, you've got to make sure your digestion, your analysis method, and your sample preparation are actually optimal in many ways. Yeah.
I love this. This is great.
Okay. Let's do the last one. Come on.
What was the last one? Should I put them back on? What was the last one?
Oh, that's gone
I
missing.
is there
Emerging tools.
Oh, let's do it. Yeah, okay. So what emerging tools or strategies do you think could revolutionize geochemical sampling over the next decade?
So there's a couple of things here. I think decreasing waste, bringing back the lost Jedi art of regolith mapping. I think that needs to have a renaissance. However, let's just call it ruthless regolith mapping. It doesn't need to be a pretty geophonological map. I don't care if you've got 4 different quaternary layers, that I'm still not going to sample them. So they mean nothing to me whatsoever. So I'm only interested in one boundary. Where do I sample? Where do I not sample? The other big thing to me is, what does a near miss look like? This is really the only thing that interests me these days in geochemistry, is what a near ore signature looks like. I know everyone knows when we intersect ore. So I'm only concerned about, what does it look like 50, 100, maybe 200 meters away? And I still don't think we've got a very good handle on that. And Scott Halley's been a fantastic advocate on that. We need more case histories of these put out in the public domain so that people are actually aware of that. 100% agree with that. I think that would be really good. And I think that focus on geochemical dispersion outside mineralization is really important. And that constitutes probably about 90% of the GM work that I do. The other thing that I'd throw in is something that's a bit of my own bent, is establishing the age of what people call transported cover. And I'm really interested in the age of that material relative to what is the last tropical weathering event. Because
Mm.
with a tropical weathering event, we can get 100 plus or 100 or so meters of vertical migration of metal. So say that occurred in the mid-Miocene, which is what we see in quite a lot of Australia. Then if we have basement mineralization that might be Proterozoic or Archean with maybe Mesozoic cover that's 100 meters thick, that material, that Mesozoic cover, could be transmissive to a geochemical signature. We do see that at the Osborne deposit in Queensland, where I was recently. So we talk about transported cover, but we don't know how old it is. And if we have that tropical weathering event that does touch basement, then we've got the chance to actually move that through. So I think we need to get a better idea on the age of cover. And I've suggested that to a group recently who are working in Argentina, because they want to go out and sample the transported cover. And I've said, do you know how old it is? And they don't. And then I said, when was the last tropical weathering event? Don't know. And I said, you're really fighting it uphill if you think you can go out and sample that material. So yeah, that's a good research project, I think, that people should actually start thinking about.
It's funny because you mentioned that the group is Argentinian, because I was thinking as you're saying all this is such a different experience that I had, because the regular transported cover that I've worked with is Andean and
Yeah.
specifically desert, part like Chile, Argentina, Peru in there. So not the tropics part. Anyway, it's just something completely different
The,
and
the
the
thing,
different families of regolith. Yeah.
exactly. And the thing is, it is now, but was it always that way? And was it that way when the material actually formed? And I've just saw something today, a post someone put up about Africa and talking about the tropical weathering occurring in Africa at the moment. And then there's a profile that's about 10, 20 meters thick. And I'm thinking, actually, that's not today. That's taken quite a while for
Yeah.
that profile to actually develop. And now I just want to know how old that material actually is. Yeah, we do have methodologies like luminescence dating to actually start looking at these sort of things.
Sure.
So even actually near where I live, which is in an area which is, I wouldn't say temperate and that sort of thing. I can go about 5 k's away and I can show you a sand dune from an arid event that happened here 10,000 years ago. Just what is there now is not necessarily how things were in the past. And I think it's a good thing if we consider ourselves geochemists, we actually
Mm.
need to start thinking more about that fourth dimension of time in terms of material that we're sampling. Yeah.
Fluids, time. Love it. Sounds good.
Cool.
It's a hashtag. All right.
Okay.
Look, so I think all that said, is there anything that you would just say to us that if you were starting your career today, would you prioritize anything? Or do you think that you did it all in the correct sequence?
Um, I think my life's motto will be, it seemed like a good idea at the time. Um, I chucked in the Dixilito missive because I think it's fantastic and a really inspiring read for young geologists to actually see what Dick has done. And probably the main thing I got out of that is Dick observes stuff and he makes his mind up on stuff based on his observations. And yeah, you can talk about who sees the most rocks wins in that regard. The other thing, last week, one of my daughters graduated from university and they had a local identity called Dr. Carl Kruseniski talk, who's a bit of a legend on Triple J, which is like the youth FM radio station. He said three things. He said, you should be curious, you should be optimistic, and you should be generous. And I look at Dick and Silito and his life. He's been curious all the way through. So keep making observations. Yeah, try and stay positive about things. Don't actually get caught up in a negative environment. And as I'm reaching the senior stages of life, yeah, I'm becoming more generous with my time and actually getting more into teaching and showing people how to do stuff. And some of that's paid, some of that's unpaid, but I'm just happy to be out there. Um, and look, if you want to become a geochemist, I would suggest the best way to do that is to get a lot of geology under your belt beforehand. And I feel that my geochemistry is augmented very strongly by the amount of rocks that I've seen. And yeah, just even things like working in potash. So I've got to work in a lot of salt in that regard. So I did a lot of seismic interpretation. This has really helped me working in sediment hosted copper, particularly in Africa, when I'm looking at the Democratic Republic of Congo type deposits and that sort of stuff. Because in a lot of the drill core, I'm starting to see salt withdrawal structures immediately, which I recognize because I've worked in potash. So the more rocks, to certainly help in that regard as well. Yeah, would I have done things differently? I don't know. If you can latch onto a traineeship, I think that's fantastic. Working underground taught me how to think in 3D before I actually got involved in 3D packages or anything like that. Yeah, grab opportunities, talk to people. Geos are generally fairly good. As Jess Keith said, besides the wonderful dancing that geochemists do, they're very friendly people as well, and they enjoying showing what they've learnt with other people and very good with their time in that regard.
Thank you, Mark. And with that, I just want to thank you for being here. And I hope that you really enjoyed talking about this topic. I loved this refresher course, this delve into different paths that I hadn't thought of before. And I hope that everybody listening really enjoyed it as well. I want to thank everybody for listening to Geochemist Tea, and a big thanks to Mark Arundell for being on the show, dishing some tea and talking about collecting samples and sampling theory. Thanks to our sponsor, IMEx Consulting and its Water and Coma Media for our music, and I'm looking forward to chatting with everybody next month.
Thanks, Sam.